So today we're going to continue our discussion of polynomials, and we're just going to start off where we stopped. Let me find that place here. Alright. Discussed was end behavior, and we said that if the degree of the polynomial is even, it's either going to be up, up, or down, down. If you have a positive leading coefficient, they're going to go left, up, right, up. If it's negative, it's going to go left, down, right, up. Now, if the degree is odd, you're going to have one go one way and the other go the other way. So if you have positive leading coefficient, you have left, down, right, up. And if you have a negative leading coefficient, you have left, up, right, down. Okay. We discussed multiplicities, the number of times a root occurs. So we said that if you're looking at a graph, you can tell the multiplicity. If it passes through once, it's going to, if it has a multiplicity of 1, it's going to pass straight through the x-axis. So for example, this could be an example of an equation for this function. So notice that we made the leading coefficient negative so that the end behavior would be left, up, right, down. And if you multiplied this all out, the degree would be 3, and it would match. Okay. We said that for an even multiplicity, so 2, 4, 6, kind of like here with x plus 4 to the power of 6, it makes a u, touches, and it comes back down. So this could be an equation for this graph. Notice that we made the leading coefficient negative so that it's down, down. Okay, if you distribute all of the factors, it will be degree 8 with negative 1 as a leading coefficient. That makes the end behavior down, down. All right, and the third one was if it has an odd multiplicity, it's going to make a snake like at 4 here. So an example of this function could be x minus 2 to the 4th, because at 2 there's an even multiplicity, and x minus 4 to the 3rd, because at 4 there's an odd multiplicity. It makes that snake. And notice that I left the leading coefficient positive so that the end behavior was down, up. When you distribute it all out, your factors, you'll have a degree 7 with 1 as a leading coefficient. Okay, so now here's our new information. I want to be able to give you an equation and for you to determine the number of complex roots. Okay, complex roots are all roots, so the real ones and the imaginary ones together. And remember that a root is a value that you plug into the equation and it makes the y equal 0. I want you to be able to determine from a graph the number of real and imaginary roots a polynomial function has. So not just the total number, but how many of them are real and how many of them are imaginary. And then last, understand that imaginary roots come in pairs of complex conjugates. So you'll see what that is in a second. All right, so I want you to pause the video and graph these 4 functions on Desmos. I'm not going to graph them for you. You need to graph them yourself. So how can you determine the number of complex roots of the function from the equation? Well, if you look, y equals 2x looks something like this. It has 1 complex root. Y equals x squared minus 3 looks something like this. It has 2 complex roots. Y equals x cubed minus 7x plus 6 looks something like this. And so it had 3 complex roots. And to the 4th power looks something like this. Actually, sorry, that was flipped because the end behavior would be up, up. So it looked something like that. So it has 1, 2, 3, 4 complex roots. So what happens is the total number of complex roots equals the degree of the polynomial. Now remember that I'm looking at the roots as x-intercepts here. So this crosses once, this crosses twice, this crosses here 3 times, this last one crossed 4 times. So I knew 1 root, 2 roots, 3 roots, 4 roots, so total, that's how many roots we have. So what happens is the total number of complex roots, so the real and the imaginary together, equals the degree. Degree 1, 1 root. Degree 2, 2 roots. Degree 3, 3 roots. Degree 4, 4 roots. And that's called the fundamental theorem of algebra, that the degree and the number of roots are the same. So state the total number of complex roots each function has. So I'll give you a second. Think about what we just learned. All right, this first one should have 5 total roots. The real and the imaginary combined would be 5. The second one should have 2 total roots. And the third one should have 4 total roots. Okay? And that just matches the degree. Degree 5, 5 roots. Degree 2, 2 roots. Degree 4, 4 roots. So now, how can you determine the degree from a graph? Well, here's those same functions. Here's this graph. So think about, how can I associate this graph with a degree 1? How can I associate this graph with knowing it's a degree 2? How can you associate this graph with knowing that it's a degree 3? And this graph with knowing that it's a degree 4? I'll give you a hint, it has to do with the curves of the graph. This has no curves, degree 1. No curves. And it's a degree 1. This has 1 curve. And it's a degree 2. This has 2 curves. And it's a degree 3. And this has 4 curves. Or sorry, this has 3 curves. I'm sorry, 3. 1, 2, 3 curves. And it's a degree 4. So some of you might have already realized that the minimum degree, so this is the smallest this degree could be 1, is curves plus 1. So if there's no curves, add 1, it's probably a degree 1. It could possibly be higher than a degree 1, but the smallest it can be is degree 1. If you have 1 curve, curves plus 1, so 1 plus 1 is 2. So this can be a degree 2. It can be also a higher degree than degree 2. We'll talk about that later a little more. This has 2 curves plus 1 is 3, so this function can be degree 3 or higher. This has 3 curves, so this can be a degree 4 or higher. If you didn't have the equations here and you just had the graphs, you would know only that the smallest this first one could be is 1. The smallest the second degree here could be is 2. The smallest this could be here is 3. And the smallest this degree of the last one would be 4. So the degree of the function, the minimum degree, is the curves of the function plus 1. So how can you determine the number of real and imaginary roots? Well, I look at this graph and I say, all right, I know that there's 2 curves, 1 curve, 2 curves. So curves plus 1 means that the degree, the smallest the degree is 3, the minimum. Now, this is a single root, so I know that x equals -1 counts for 1 of those 3 roots. This is a double root here, so I know x equals 2 actually counts for 2 roots. It could count for 4, 6, or 8. We're talking about minimum here. This is an even multiplicity. Remember when it does a u and it touches. So I have -1 counting for 1. I have 2 counting for 2 of the roots. So here's 1, 2, 3. Well, that's all of my roots, because remember that the degree of the function equals the number of roots. So what happens is real roots equals the x-intercepts. The imaginary roots equals the rest. So the minimum number of complex roots here is 3. We had 2 curves plus 1 was 3. There are 3 real roots. 2 x-intercepts, one with a multiplicity of 1 and the other with a multiplicity of 2. So those 2 x-intercepts actually count for 3 of the roots. Now because there's 3 total roots and we had 3 x-intercepts, what that means is that there's none left over to be imaginary. So there are 0 imaginary roots. If there are 3 real roots, then there are none left over to be imaginary. Okay, let's look at another example. Here. So I know that the degree of the function is curves plus 1. So we have 1, 2, 3 curves plus 1. That's 4. So the minimum degree is 4. Now I look here and I see, okay, I have an x-intercept here and an x-intercept here. I'm not quite sure where those are. 1, 2, 3, 4, 5. This is like negative 4 point something, and this is like negative 3 point something. But those two roots only count for 1 each. So I'm going to say counts for 1. And this one also counts for 1. And that's because they have a multiplicity of 1 because they go straight through that x-axis. But the degree is 4. And this counts for 1 and this counts for 1. So I know I have two real roots, the ones that I can see as x-intercepts. That must mean that the other two roots are imaginary. And imaginary roots you can't see because what we're doing is graphing on a real coordinate plane. So we said the real roots are your x-intercepts, so those are those points on the left. And the imaginary roots are the rest. Minimum number of complex roots is the degree, which is the curves plus 1, so we said that the minimum degree is 4. We have two real roots, two x-intercepts, both with a multiplicity of 1. And now that means that the other two roots must be imaginary. And you don't know what they are by looking at the graph. You just know that there's two imaginary roots. Okay? Now, before we get to this, I want to look at one other example with you guys. So, I'm going to add a picture. Okay, let's say I have a graph that looks like this. And it kind of looks like a cubic. Students sometimes make a mistake here because they're like, okay, what are the curves? Well, the degree here is curves plus 1. Well, this counts as one curve, and this counts as another curve. So if ever you see a function where it kind of snakes like this, both of these where it goes from kind of facing down to facing up, being like a frowny face here, like half of a frowny face, to being half of a smiley face, each one of those counts as a curve. So the degree here is 2 curves plus 1 is 3. The real roots, there's one real root right here where it cuts straight through. And that means that the other two must be imaginary. Okay, so total roots are 3. One of them's real, the other two must be imaginary. So remember that whenever you see this where you have like a snake, each part of that curve counts for one curve. So 2 curves plus 1 is degree 3. All right, last concept here. Imaginary roots always come in pairs of complex conjugates. What does that mean? So remember in Algebra 2 where we had stuff like 2 plus 3i, and we were like, what's the conjugate of that? Well, the conjugate simply changes the sign in the middle. So what we're saying is that if one is a root, the other is also a root. So for example, if 3i is a root, then negative 3i must also be a root. If 2 plus I is a root, then 2 minus I must also be a root. Now you might be asking yourself, why? Well, the reason why is that, let's say you have x equals 1 and x equals 3i as roots. Okay, you don't have its complex conjugate, you just have 3i. So if 1 is a root, x minus 1 would be a factor, and if 3i is a root, x minus 3i would be a factor. If I distribute that, I end up getting y equals x squared minus 3ix minus x plus 3i. And there's nothing else I can combine together here. I end up with imaginary numbers in my polynomial. There's no way that you can graph this polynomial with imaginary numbers on a real coordinate plane. So we always have real numbers for coefficients when we're talking about polynomials. So you cannot have imaginary coefficients in a polynomial graphed on a real coordinate plane. So we can't have this 3i. We can't have this 3i here. So that means that if we had x equals 1, x equals 3i, and x equals negative 3i, now watch what happens because we have both of these as roots. When we create the function, we start out here. We start out here. We have x minus I, x minus 3i, x plus 3i. Now, if I distribute into the second, I get x times x is x squared. And then I have plus 3ix. Distribute on the top, we get minus 3ix. And then minus 9i squared. Now, from algebra 2, you know that I squared is really negative 1. And 3ix minus 3ix cancels. So we have x minus 1 times x squared minus 9 times negative 1, which gives you this guy here, x minus 1 times x squared plus 9. If you distribute everything in, you end up with this polynomial. Notice that you have no imaginary coefficients. And that's because up here, when we double distribute with the conjugates, it gets rid of that imaginary part. So notice all of the coefficients are real numbers. So what you need to know is that always you're going to have the imaginary roots come in pairs, and they're going to be common. And that is it.